Okay, so we're going to carry on with chapter seven now. So far we've done sections seven, one, and two. And in those two sections, we did the disk method and we did the washer method. Now it's time for the shell method. Okay, so each one has its own place in these cases where we're trying to figure out an area or a volume, possibly. Usually the volumes are found by rotating or revolving about either the horizontal or the vertical axis, although they can be revolved around any axis that we choose. So here we're going to look at the shell method rather. And so this one is a little bit different. We'll start with this first basic case, and you can see that there's a reason for it being called a shell. You're looking at essentially a hollow tube, and so we need to keep track of several details as far as the geometry goes. So why don't I start by copying this into my notes? Yeah, there's a lot going on with this one. So the reason why this one is so complicated is because the P, remember now the P, remember, is supposed to be the distance between the center of the representative rectangle and um, the axis of revolution. But here that isn't the same on both sides. If you notice, there's an outer part and there's an inner part. So we've got P and P minus 2, or sorry, P plus W2. Let me write this down somewhere. And that reaches us to the very top of our cylinder. And this is the just goes to the interior of the cylinder. And so the way they've set it up, W is the width reaching from here to here. So because of the way they've set it up, this P that we'll be using in the formula is actually the average of these two. So instead of the actual distance from the axis of revolution to the representative rectangle, it's the average. Okay, so we have to interpret it just a little bit differently. So it's the average distance now from axis of revolution, which in this case is going to be this. It doesn't specifically say that it's the horizontal axis because it doesn't have to be, but it might be the horizontal axis. So, but it's the axis of revolution. And if you notice, they're trying to help us here. You see this little blue arrow. It's supposed to remind us that we're going from top to bottom, basically. All right. So then the rest of it is pretty straightforward. H is the height, as it's always been, of the representative rectangle, which is this sort of reddish region here. Um, all right. So how do we get the volume? All right. So the formula is coming up next. Um, here we go. So they're letting you see that they're thinking of as the volume of the cylinder on the left, where W plus 2 is the outer distance to the axis. And then here's the volume of the whole. W P minus W over 2 is the inner distance just to this top region here, the interior part. And so what they're going to do is consolidate these into this expression where we end up with 2 pi average radius, height, and thickness, or in other words, um, using the notation we started to use in the earlier sections, delta V is 2 pi P of H, H of Y, and delta Y. Okay, now whether we're using, as you recall, Y or X depends on which axis we're rotating around. Okay, and the approach to that is different between disk and shell. In fact, there's a graphic here to remind you about this. Um, let's take a quick look at it. So with disk, the representative rectangle is perpendicular to the axis of revolution. So if this was the disk method, we'd have a horizontal representative rectangle and we rotate it around the x-axis. Okay. On the right, if we had the opposite, if we want to rotate around the um, vertical axis, um, let's see, let me look at this really closely. It's hard to see some of these perpendicular, right? Okay, so in other words, let me sketch this in a little bit better, just so I can write on it. So we're always keeping an eye on these little arrows. So the way you have to think about it is that this is the axis of revolution. And of course, this is the representative rectangle. You can see it's lying on its side. It's facing, it is, you can think of it as being perpendicular to the axis. Okay. Over here on the right, if our axis of revolution is here, well, then we must have a vertical representative rectangle. Okay. So over here, it's horizontal. Representative rectangle. And that, by the way, that also implies that all the variables are in terms of y. Like, for example, the width is delta y. You can see it here. Um, and also the endpoints are on the axis of revolution, whereas over here, it's the other way around. Okay, so you notice how the representative rectangle has a width of delta x, okay, because it's with respect to the horizontal axis around which we're now going to rotate it. And also, just a quick reminder, with this one, we're looking at capital R, which is the outer radius, and little r, which is the inner radius. And over here, we find them, the inner radius is here, and here's the outer radius. Anyway, so this is disk. They want to remind you how this works so that you can see how it's different from shell. Shell just means that the represented rectangle is parallel to the axis of revolution. Okay, that's the main difference. So I think they have a graph of that right here. Why, yes, they do. Okay, let's take a look. Now, what that basically means is that pretty much for any case where you could use disk, you could also use shell. Um, it's you can always go either direction, but anyway, so here's shell, and now if you notice, we're going to rotate. Um, sorry, I was looking at the wrong thing. It's going this way. We're rotating or revolving around the vertical axis. So therefore, we're going to have a vertical representative rectangle. And that just means everything's in terms of x. Okay, delta x is the width. Now remember, now this one is pitched a little bit differently. We don't have any radius measures. We have a height and we have p. P always means the distance between the center of the representative rectangle and the axis of revolution. Okay, so that's where this is coming from. And then, of course, the height. H is very simple. It's just the height of that rectangle. And of course, the endpoints here are defined with respect to X. Here they're defined with respect to Y. All right. So that's really the big difference between the two. Which way are we going? Is the rectangle tells us in one case it's perpendicular. In this case, it's parallel. Okay. But the basic logic is exactly the same. All right. So with all that being said, let's go back and look at an example. All right, here we go. So these are the formulas that we'll use in both cases, depending on which axis we're revolving around. Okay, so we'll keep these handy as we go along. So we'll start with this one. So we have this function, y equals x minus x cubed. Why don't we take a quick peek at Symbol Lab? Okay, now this is 1, 0. So it looks like they only want us to focus on this little piece here that is above the horizontal axis from 0, 0 to 1, 0. There it is. All right. So yeah, that's what this is. All right, great. All right, let me copy this graph and make it a little bigger. Yeah, that's better. So they're telling us in the problem, the function is x minus x cubed. And they want us to use that, of course, and they would like us to revolve about the. Okay, so you have to read these very carefully. They want us to restrict our attention to 0 to 1, fine. And but the axis of revolution is actually the vertical axis. Okay, right here. And so because it's the shell method, if you notice, the representative rectangle is in fact parallel to the axis of revolution. That's what we need. So therefore, now everything is in terms of x's when we do the integral. And so delta x is the width. P of x is simply the distance from here to here. We're going to call that x. And then the height is just the function. Okay, whatever the function is, that would be the height because it's all with respect to the horizontal axis. Okay. If there's a gap in there somewhere, we'd have to do something different, but there isn't. So what formula are we using? Let's go back. That would be this one. All right. So again, we already know P of x is x in this case. H of x is x minus x cubed. Now, what about the endpoints? Well, that's easy because they told us to restrict ourselves to 0 to 1. Okay. Sometimes we have to figure that out ourselves. Yeah, we got lucky here. Okay, so all we have to do is make some substitutions. Now, this is not a very difficult integral. As long as we're careful, should have no trouble with it. So what this illustrates is that really with these problems, the biggest issue is setting it up. The integration is nothing by comparison. Setting it up is the biggest headache. Okay, so they have to tell you whether it's disk or shell. They have to tell you the region that we're looking at and which way to rotate it. Once they've done that, we should be able to pick out the correct integral and then fill it in and then take care of the rest. Okay, so let's run through this real fast. So we'll multiply everything out, x squared minus x to the fourth. Then we'll we'll do this. Break it up into two separate integrals. Now, this isn't absolutely necessary. I just kind of like to do it this way. When they get messier, then that's different. Here it isn't really necessary, but anyway, let's see what we get. So the first one, once we integrate using the power rule, we'll get x cubed over 3. All right, our old friend, the power rule. Let's quickly review it. The power rule for integrals. And if it's a definite integral, we don't need the c. We'll just evaluate it, which is what we're about to do here. And so we'll start here. All right, we could factor out those constants, but since this is such a simple case, it may not be necessary. So in other words, what we have here is 1 cubed over 3 minus 0 cubed over 3 minus 1 to the fifth over 5. Oh boy, hold on, let me fix that. Yeah, okay. Minus 0 to the fifth over 5. All right, what does that leave us with? 1/3 minus 0 minus 1/5 minus 0. Now, of course, we'll need a common denominator here. Let's do 15. So we have 2 pi times 2/15, and we end up very simply with 4 pi over 15. And we're done. Okay. So that wasn't too painful. I think you'll agree. Beautiful. Okay. Now here, as we've already discussed, they're showing the difference between the two approaches. Most likely, you'll choose the one that leads us to the simplest integration to take care of, because integration can get extremely messy. And if one of these approaches is simpler than the other, of course, we'll run with it. But they're making it clear that we can do either one. Now, where they're showing you where the shell method is very helpful. We've already seen this example of the washer method, where we had this very messy expression, this whole thing under here, that had to be revolved about the vertical axis. And in order to do it with the washer method, we had to break it up into two regions and do them separately, which is, kind of a lot of work. So let's just quickly remind ourselves how the washer method is defined and remind ourselves how this worked. All right, so the washer method, you remember that it's defined in terms of something like this. Okay. Well, actually, it'll become this shape after we've rotated it, but it looks like a washer, like something you need to screw things together. I can't explain it any further than that. If you've seen one, well, uh, uh, we could look it up on the internet, I suppose. Anyway, so here's how that works with the washer method. There's two possibilities. So the logic here is that whatever the rectangle is, it's not going to quite reach the axis of revolution. And we're defining this as W. So the volume that we need to create this kind of thing, um, the diagram, I wrote down the diagram so I didn't forget the parts of it. Um, this this is supposed to be the result of spinning it around. This is the best I can do. Um, so this stays as little r, this is capital R. Yeah, they had a better graph in the slides, but anyway, so what you have to do here is this. So that was the washer method. Okay. So what they're reminding us here is that in order to do this properly with this particular situation, we had to break this up into two regions. And you can see that this is how they handled it. The one on the bottom is a rectangle. So yeah, let's copy this again. And yes, we definitely did this the other day. And so here they're telling us that, at least in the bottom half, the axis of revolution is the vertical axis. So we're revolving around it. And that means there is no lowercase r. Okay, we're already at the the axis, but the capital R would be here. And then we just integrate. In fact, here it's just a rectangle. We don't even have to bother with integration if we don't want to. Up here, you can see the lowercase r. The uppercase r is still here. And the range of values for y is 1 to 2, which you can find by plugging in the x's into the function r equals radical y minus 1. So they ended up with this result. Okay. And, and again, we've already been through this, but let's just quickly run through it one more time. So this is the region on the bottom that looks like a rectangle. And since we're rotating in this direction, everything's is done with respect to y. Okay. So actually, I did this incorrectly. Then I should have written this as y here. Sorry. And for the other rectangle, oh, well, the other region, the capital RY didn't change. This one is different because this is the original function. All right, and then the rest is just straight ahead integration. We went through all the steps, and we ended up with 3/2 over 2, 3/2 pi over 2. So what they're saying here is that this is a classic example of when you might be better off using shell because you only need one integral. Okay, so here's how they're going to do it with shell. So here they're saying, listen, this is why we have all these techniques because sometimes one of them will be more convenient than the other ones. So here, remember, the rectangle here is going to be parallel to the axis of revolution. And so it's vertical and everything's in terms of x's. We have delta x is the width. That p, remember, is the distance between the axis of revolution, which is the vertical axis in this case, and the center of the representative rectangle. And that in this case is just x. Okay. And now the height, now this is the function. Remember, the top part, at least, they defined it here somewhere. Well, in the original problem, it was given to us as x squared plus one. You can see that it closer is, I mean, that means you're simply looking at the parabola. This is y equals x squared plus one. And it's a parabola that crosses the axis at one. And so we're only interested in the region between 0 and 1, this piece here. Okay, great. Now my drawing isn't very good, but that's why it looks like this. Okay. So anyway, so the height is the function. H of x is here. The height of the representative rectangle. And then the upper and lower limits of integration are the x coordinates. And so we see that with the shell method, when we're revolving about the vertical axis, um, let's come back here for a second. That's this case. Okay. So what will that leave us with? All right. Yeah, so this is it. They did a good job here. It's that's the function that we use when we're revolving around the vertical axis because everything's in terms of x's. And so let's write that down. 2 pi a to b. So remember, the way they've been writing these, a and b are supposed to represent x coordinates, c and d are y coordinates. Okay, then we have the p of x, h of x, dx, and then we just plug everything in. P of x was just plain x. H of x was x squared plus 1 dx. Now, again, this is a very straightforward integral. Although, by the way, I just want to mention that in chapter 8, we're going to introduce the really complex integration formulas. We know the basic ones. We're going to be introduced to the really advanced ones in chapter 8. In fact, the whole chapter is just one integration technique after another, but you have to know them. You have to know them all, especially if you're going on any further. So that'll be chapter 8. But here, this is a very simple one. We're just using the power rule for each term. And then we're using the fundamental theorem of calculus to solve for it. Okay. So then we just carry on with the power rule. All right. And then that will leave us with. So we have here we have 1 to the fourth over 4 minus 0 to the fourth over 4. Here we have 1 squared over 2 minus 0 squared over 2. Okay. See, I just realized I have to be very careful with these exponents. Writing on this screen, I notice I'm tending to make them too low. It's very different than the whiteboard, so I have to be careful with it. Anyway, we have 2 pi, 1 fourth minus 0 plus 1 half minus 0. And we have so if I convert these into quarters, you'll see that we end up with 3 quarters. and we end up with 3 pi over 2. I skipped a few steps, but it's 3 pi over 2. Okay, there it is. Beautiful. So I think they're trying to make the case here that maybe at least here, when you've got a particularly unusual shape, you're probably better off using the shell method instead of trying to split it up into separate regions like we had to do the other day. So that is their argument in favor of this method. All right, so now at the end here, we have these two knowledge checks. They're going to test our knowledge about the shell method using, in one case, the revolving around the horizontal axis, and in the other case, the vertical axis. So again, the whole thing is all about setting it up correctly. So let's try this one. The integrals are easy. Oops. Wait a minute, what just happened? I'm just making sure I didn't lose anything. That's one of the risks of the handwriting. It can get distorted if we're not careful. Let me try that again. All right, that's better. All right, so this looks like it's intact. All right, that's good. We should be okay. Yeah. You never know what can go wrong with technology. It's just, all right. Also, but we need more information than that because they're telling us, first of all, to use the shell method. They have to tell you. If they want you to use one specific method, they have to tell you that. Um, we're going to revolve about the x-axis. Okay. Now, this is a particularly simple one because it's just a straight line. And they want us to revolve it around the x-axis. So I'll tell you what they're not doing. They did not give us a nice little graph of what it looks like when it's done. Um, it's hard to visualize. I don't know. It's going to be some kind of weird conic shape, I suppose. But what they really want us to do is set it up correctly. So let's do this. Now, this is shell, which means the representative rectangle is going to be parallel to the axis of revolution, which is itself the horizontal axis. That means it's going to look like this. Here's our delta y. And that means all the variables are in terms of y. So we have to keep an eye on that. So then we have the limits of integration are going to be in terms of y from here to here. And so the p will be here. And the h will be here. Okay, so the C and the D are easy. C is clearly 0. D would be 10 because if you're not sure, remember what we're solving for is what is the value of y when x equals 0? That's where this is coming from. All right, so that was the easy part. The delta y, right, it is what it is. Now, h is based on that function. Now, here's the thing we have to watch out for, though. The function is written as y equals 10 minus x. In order to do this properly, this is the tricky part. We have to rewrite it. Oh. So that we can say that h of y is 10 minus y. P of y is just y. Okay, that's the height. So remember the formula that they have us use. Let's go back and revisit the charts that they gave us, or graphs rather. Aha, it would be this one. Oops, no, sorry, that's disk. Sorry. Um, where's the shell? Here we go. No, no, wait a minute. Sorry, this is disk. This is shell. Okay. So in other words, we're looking at this case. Well, all right, I'll copy them both, but we're looking at the case on the right. All right, this is what we're trying to do. All right. So we have, okay, but we have all that information. We know that, oh, wait a minute. I forgot the 2 pi. Sorry, hold on. I knew something was missing. Can't have a volume without pi, can you? So we'll just substitute. Now, we already know that P of y, we've from our graph, is y. Um, yes, y. And h of y, remember we rewrote this to be 10 minus y. That's kind of the weird part about this. If you hadn't done this before, you'd never think to do something like that. It all has to be functions of y. Okay, well now we're good. The rest is easy. All right, so we'll just use the power rule. And then we may have to simplify it a little bit. Like, yeah, why don't we do this? Let's get those pesky constants outside. Like this one, 10 over 2 is just 5. Okay, that should do it. All right, and then we have, so here inside the parentheses, we have 100. And then we have 1/3 of 1,000. Okay. So I'm going to multiply out this 2 pi across here. So I'll have 10 pi times, oh, yeah, that's right, 10 pi minus 2 pi. All right, so what do we have here? 1,000? Over here we have 2,000 pi over 3. So we'll need a common denominator of 3. And that's 1,000 pi over 3. Whatever that volume looks like. Um, God, I don't think I'd even ask Symbol Lab to try it, but it's the area, the volume rather, is 1,000 over 3, 1,000 pi over 3. All right, let's confirm that. Oops. And so that would be C. Oh, okay. So they've got two choices. Oh, I see. They've got 10. All right, then it must be D. Okay, whatever they say. All right, I don't know why they did it that way, but it's correct. All right, good. Now here they're going to have us do the opposite. They want us to revolve this around the not the vertical axis, but a vertical line. So let's see how this one is set up. Um, Use the shell method. Volume of the solid. So it's y equals 2x cubed. Y equals 0. This is the area of interest. And we're going to revolve around x equals 8. All right, so we should be able to get a fairly good idea what this looks like. A y equals 2x cubed would look like this, roughly. And we only care about 0 and 3. But the axis of revolution is way out here somewhere. So it's going to go this way. Okay. Um, wow, that's strange. So in other words, the axis, oh, wait a minute, sorry. No, that's right. It does say to revolve around x equals 8. So what I meant is the rectangle will be here. Then we need a height, which is simply the function. And now here, though, 8 minus x. Now each rectangle will be in a different location, so it's always x minus 8 minus x. Okay. So which integral are we using? This is the one that's written in terms of x's. Okay. All right. I have to pause now. I have to take this phone call. Sorry. Oh, crap. Hello? Hi, yes. Yes. All right. Sure. All right. Okay, I'll see you then. All right, bye. Wow, that's the first ha time that's happened this summer. I usually don't get important phone calls while I'm doing this. But that was a biggie. That was my dentist. So, I had, all right. Anyway, let's get back to this. Let's fill in all the numbers. Okay. Oh, you know what? I forgot to fill them in. A is, we have 0 and 3. Okay. 8 minus x, 2x cubed dx. This, of course, is our p of x. This is our h of x. All right. And like I said, this is a very straightforward integral. The biggest headache is getting it set up. If you can do that part, the rest of this will just fall right into place. Let's multiply this out. We have 16x cubed minus 2x to the fourth dx. All right, we're multiplying 8 and negative. Yes, that's right. Then we'll break it up. Right. Using the power rule and the fundamental theorem of calculus, we'll get our answer. All right. And of course, we can simplify it a little bit as we go along. Good. All right, that should do it. So this is 3 to the fourth minus 0 to the fourth. All right, so then we have, so 3 to the fourth is 81. 3 to the fifth is 243. All right, so we'll have to clean this up a bit. All right, so of course now we'll need a common denominator. 5 times 324 would be 1620. And God, what a mess, huh? All right, I don't want to push my luck. I'm going to take out the calculator. 2268 over 5 pi. All right, so there it is, A. Okay. Ta-da. Okay. Now, so that was 7.3. Now, 7.4 is a little bit different. What they're going to have us do, let me get this thing open. That's 3. Oh, I thought I had it here somewhere. All right. So, whatever it is, there's something involving, we're going to look at arc lengths among other things. It's a little bit different, but it's definitely an application of integration. So, I think maybe we'll wrap it up here, and then we'll do 7.4 next time. And then finally, we can get to chapter 8, which is where we're going to get to see all these very powerful integration techniques. And so that's going to take us a while. But when we're done, we'll be experts in integration. Okay. So I'll see you next time.